Hey everyone. This last video is a brief primer on causal inference and the potential outcomes framework. So to start, what do we mean by causality and causal inference in social science research? And in this context, it's important to conceptually first differentiate between the effect of causes and the causes of effects. And in most social science applications, we're ultimately, the way we ask research questions are not asking questions about the causes of effects. So in the sense, for example, asking what causes person X to vote for one party rather than the other. But rather the effect of specific causes, right? So we're looking at a specific cause, and what we're trying to, for example, party identification, and we're trying to estimate is what the effect of that cause is on our outcome of interest. So, for example, voting for Democrats rather than Republicans, Democratic candidates rather than Republican candidates, right? So when we talk about causality and when we talk about causal inference, what we mean and what we focus on is trying to estimate the effect, accurately estimate the effect of causes, and not necessarily, identifying the causes of a specific effect. Okay. And in order to identify the effect of a specific cause or the effect of a specific manipulation or treatment, what we need, or what that kind of quantity is always based on, at least conceptually, is a comparison between some factual outcome and a counterfactual outcome. If, for example, if we think about binary treatments, that treatment was present or if it wasn't present, right? So the comparison between factual and counterfactual is the fundamental basis for our understanding of causality and causal inference. And as I mentioned before, in this context, some relationship or association does not necessarily imply causation, right? We're not just looking at the correlation between specific outcomes, but that kind of that type of association itself is not sufficient. Okay. Another important aspect that is useful to keep in mind is that in this context of causality as a comparison between a factual and a counterfactual, that also implies that it's not quite straightforward to think about causation or causal effects of characteristics that can ultimately not be manipulated, right? So as soon as you have immutable characteristics that cannot be changed, it's much more difficult to think about to think about causal effects. Or to estimate the causal effect of something. Okay. There are two main approaches to kind of characterize and conceptualize causal inference. One is the causal graph framework, and the other one is the potential outcomes framework. And in this video, I'm going to just focus on the potential outcomes framework. So as I mentioned, causal inference is ultimately based on a comparison between a factual and a counterfactual outcome, depending on some treatment assignment. Okay. So the potential outcomes framework basically provides us with a framework to kind of to characterize these differences between counterfactuals in kind of a systematic way. Okay. So what does the potential outcomes framework ultimately imply? There are three main elements of the potential outcomes framework. The first one is that there are different units. So these are kind of the observations that we're interested in. So, for example, in the context of the draft lottery in 1970, that would be people who were eligible for military service in the United States. And then we have treatments. And so a treatment is ultimately the kind of the manipulation or the intervention that we want to estimate a causal effect for. So again, in the context of this example of the military draft, the treatment would be whether a person served in the military versus not. Okay. And then lastly, the third element are the potential outcomes. So those are basically the outcome we're interested in. So in this kind of running example, it would be the earnings in the Angress study. It would be the earnings in 1978 of a person if that person either served in the military or did not serve in the military. Okay, so the important thing to note here is that there are basically two possible counterfactuals for each individual unit, right? So in this table we have each row is one person or one observation, and for each observation we have two potential outcomes. Y1 or for treatment assignment 1 and treatment treatment and control, right? So these are kind of the counterfactual outcomes, so the counterfactual earnings in our example for a person who did serve in the military versus a person that did not serve in the military. Okay. And if we were able to observe both kind of the earning conditional on that person serving in the military versus the earning conditional on the person not serving in the military, we could kind of define the treatment effect. So the difference between earning under military service and not military service as tau. Okay, I should actually continue with the slides as well. So we have two potential outcomes for each observation, Y under treatment and Y under control. In our case, serving in the military versus not. The causal effect for each individual I is then defined as tau I, which is just the difference between these two potential outcomes, right? So that's the difference between the counterfactual of earnings having served in the military minus the earnings of not having served in the military. So based on this framework, we can define the average causal effect across all individuals. So that's the ATE, the average treatment effect, as the expectation of tau I. So that's just the average of all tau I's across all individuals. Okay. And ultimately, we can kind of split up the sum. This tau I, of course, is the difference between yi1 minus yi0, so the outcome under treatment minus the outcome under control. And we can separate this sum into basically the first component here being the average earnings among all for all potential outcomes for all individuals in the treatment group minus the average outcome or earnings in this case in the control group. Okay, so this seems pretty straightforward at first, but the important problem is that, of course, obviously, we don't observe both potential outcomes. And this is what is called the fundamental problem of causal inference, which is that only one of the two potential outcomes is observable for every one observation. So rather than having this table where we have, the potential outcome for treatment and control for each observation, and we can actually compute this treatment effect, what our data usually only looks like is one realized potential outcome for, depending on whether that person was in the control group, as here row 1, or row 2 in the treatment group. So we can actually compute the treatment effects for each individual observation, and therefore not, without making additional assumptions, estimate the average treatment effect. So the fundamental problem of causal inference ultimately just means that causality is defined based on the comparison between the factual and the counterfactual, but the counterfactuals for each individual, of course, are not directly observed. So what we need ultimately is a credible way to infer the unobserved counterfactual outcomes, and this is where kind of a lot of important assumptions come into play, and ultimately causal inference rests on whether these identifying assumptions are ultimately plausible. So if we want to kind of figure out what these counterfactuals are, or if we want to kind of figure out what kind of assumptions we need to make in order to identify these causal effects, it's kind of helpful to first think about the gold standard, which is a true randomized controlled trial, so a true experiment. Okay. So here the key idea, of course, the fundamental problem of causal inference still exists for a true random experiment, but the key idea is that randomization of the treatment makes the treatment and control groups basically identical on average. And that is important because if treatment and control groups are identical or almost identical on average, that means they're similar in terms of all both unobserved and observed other characteristics that potentially influence the outcome variable, which implies that we can attribute the average differences in outcomes to the actual difference in treatments, because there are no other systematic differences between both groups. And kind of to just show this formally using the potential outcomes framework, if random assignment holds, what we can say is that the potential outcomes in the control group as well as in the treatment groups are independent of the treatment assignment. And if that is the case, that means that the expectation of y in the treatment group, conditional on the treatment, or conditional on the observation actually being assigned to the control group, is exactly the same as the expectation of y in the treatment group, conditional on being in the actually being assigned to the treatment group, right? So you have to kind of think about this in terms of course, potential outcomes, which are not necessarily observed. But the way to think about this is that the outcome, had someone been assigned to the treatment, but is in the control group, is the same as the outcome for observations that were actually assigned to the treatment. Okay. And if that holds, that means that the both are equal to the expectation just of the outcome variable in the treatment group marginalized over both assignment to treatment as well as assignment to control. And the same holds, of course, kind of equivalently for the control group. Okay. So if these hold, so if the potential outcomes are independent of treatment assignment, and both potential outcomes are equal across treatment and control assignment, then we can express the average treatment effect as the simply the average or the expectation of the outcome conditional on being assigned to the treatment minus the expectation of the outcome conditional on being assigned to the control. And this is simply, if I go back, the difference in mean estimator, basically, or I should go here, basically just looking at the average across all observations who were in the treatment, looking at the average of the outcome minus the average of the outcome of all observations that were assigned to the control. And since it doesn't matter for the potential outcomes whether someone was actually assigned to treatment or control, we can just average the observed treatment and control values and compare their difference to estimate the average treatment effect. So this is kind of the gold standard, or how randomization and randomized treatment allocation helps us identify or kind of overcome this fundamental problem of causal inference. There are a couple of kind of crucial assumptions that we have to make as soon as we deviate from this gold standard. And the first one that is often mentioned is this question of ignorability. Ignorability is exactly this assumption that we have random assignment, and it implies that the treatment assignments are statistically independent of the subject's potential outcomes. In order to kind of show you how this violating this can ultimately induce what we call selection bias, I'm going to go through one quick example here. Here, what we start with is the basic specification of the average treatment effect. As you see here, the average treatment effect we defined as the difference in the outcome in the treatment group minus the outcome in the control group. And this is the same equation here up to this point. Now we can kind of use a little trick and add two terms. The terms that we are adding are here. We subtract the expectation of yi0, so the potential outcomes in the control group, or the potential outcomes if you haven't received the treatment but you were assigned to the treatment group. And we first subtract that, and then we add this, the same term, which of course these two would cancel out and would be equal to 0. And then we subtract the outcome for the control group, right? So we didn't really change any math here. We just added a term and subtracted it immediately thereafter, okay? We can rearrange this though. And the reason why we want to rearrange this is we can basically kind of group the difference between treatment and control for assignment to the treatment condition in one expectation, and then separate out the expectation of yi0 under assignment to the treatment and yi0 under assignment to control. And basically after we separated these out, we kind of decomposed the average treatment effect that we started with into the average treatment effect among the treated. So this is basically the difference between the potential outcomes of treatment and control among those who were actually assigned to the treatment. So that's the average treatment effect among the treated, and the remaining difference in potential outcomes between observations that were assigned to the treatment and observations that were assigned to the control for the potential outcomes that didn't receive the treatment. And this is ultimately, we can call this the selection bias, right? So ultimately, kind of this rearranging and this little trick of adding and subtracting the potential outcomes in the potential outcomes for the control condition kind of helps us to re-specify the overall average treatment effect as a composition of the average treatment effect among the treated and the selection bias. So if ignorability holds and there is no difference between the control, the potential outcome for the control in the treatment group and the assigned control group, then this selection bias is zero, it cancels out, which implies that the average treatment effect among the treated is equal to the average treatment effect among the entire population, or the entire sample. A second crucial assumption for causal inference that we read about a lot is excludability, and that is also discussed in the chapter. Excludability implies that potential outcomes respond solely to the receipt of the treatment and not to the random assignment of the treatment or any indirect byproduct of random assignment. So that means it's violated when for example, different procedures are used to measure outcomes in the treatment and control groups, or if research activities, other treatments, or third-party interventions other than the treatment of interest differentially affect the treatment and control groups. So in our example of the military draft in 1970, the example of violating the excludability assumption would be people who are drafted for military service spend more time in school in order to avoid service, and ultimately this would lead to higher earnings later on, right? So this would be the treatment assignment ultimately affecting the outcome through a different mechanism than the main mechanism we're interested in, which is kind of whether someone served in the military versus not. Another important assumption that is often discussed is non-interference, or SUTVA, which stands for the stable unit treatment value assumption, which just a second. Which means that potential outcomes of observation I reflect only the treatment or control status of observation I and not of other observations. So essentially, in other words, what that means is that the treatment of one subject does not affect the treatment of other subjects, or assigning one observation to a treatment doesn't interfere with the treatment assignment of another observation. So this can be violated when subjects are aware of the treatments that other subjects receive, or that treatments may be transmitted from treated to untreated subjects. Or lastly, if resources used to treat one set of subjects diminishes resources that would otherwise be available to other subjects. A last aspect that I want to talk about briefly, that is also discussed in the bit-by-bit book, is the question of compliance, specifically in the context of natural experiments. Because ultimately assignment to a treatment group does not always imply that the treatment is actually delivered, right? In the example of our draft lottery that we talked about, we could think of the draft lottery itself as a randomly assigned secondary treatment that encouraged some people to take the primary treatment, which is actually serving in the military, right? But not everyone who, as we know maybe from today's politics, not everyone who was assigned to the draft ultimately had to, or who was picked in the draft lottery ultimately had to serve in the military. And so if we want to think about whether people who are assigned to the treatment actually received the treatment, we have to kind of differentiate between 4 different groups of observations or subjects. And these are compliers, never takers, defiers, and always takers. And what differentiates them is that compliers can be characterized as people who, if they were assigned to the treatment, actually also kind of took the treatment. So they were picked in the draft lottery and they went to the military service. Never takers are observations that would never, under no circumstance, actually take the treatment. So even regardless of whether they were drafted or not, they wouldn't go to the military. Defiers are people who always do the opposite of what the treatment assignment mechanisms says. So ultimately, those are hypothetically individuals who would only go to the military if they were not assigned to, or if they were not picked by the draft lottery. And then always takers are observations that always take the treatment. So they would, go to the military regardless of whether they were picked in the draft lottery or not. Okay. In cases where we have an encouragement design, so we don't have perfect compliance and we only assign people to be encouraged to take the treatment, to go to the military in our example, what is often used is what is called the instrumental variables approach. And in the context of instrumental variables, it is important to kind of differentiate between, on the one hand, the intention to treat effect, the ITT, which is kind of not the effect of the treatment that we're actually interested in, like going to the military, but it's the effect of being encouraged to go to the military, right? So we can directly, by looking at differences in between treatment and control, or difference between picked in the draft lottery and not picked in the draft lottery, directly tells us something about the effect of being kind of included in the draft, but not necessarily directly tells us something about the effect of serving in the military. So this is the intention to treat effect. That's the effect of being assigned to the treatment group, irrespective of whether that person actually complied and received the treatment. And then we have the complier average. The complier average causal effect, which is ultimately the effect of the, in our example, the effect of serving in the military versus not serving in the military among respondents who complied, who complied with the treatment assignment. Okay. And we can identify this complier average causal effect, or the local average treatment effect, if we assume that we have perfect random assignment. We have to assume that there are no defiers, so no people who kind of just always do the opposite of the treatment assignment, and we have to assume that the exclusion restriction holds, which means that there's no kind of additional mechanism through which the treatment or the encouragement to take the treatment affects the outcome of interest. And if those hold, then we can we can estimate the Complier average causal effect, which is ultimately the difference in outcomes the difference in outcomes between those who were encouraged and those who were not encouraged. So that's the ITT, the intention to treat effect on the outcome, weighted by or inflated by the uptake rate. So that's kind of the extent to which the encouragement to take the treatment actually increased the uptake. So actually increased the extent to which people took the treatment. There are two important caveats. The first one is oopsie. Wait a second. There are two important caveats. The first one is the exclusion restriction is a strong assumption, and it needs to be justified on a case-by-case basis. So in many applications, it doesn't necessarily hold. And then second, with instrumental variables approaches, instruments are often not or too weak, so they're ultimately not a strong enough predictor of actually being exposed to the treatment or not, which can make it difficult to reliably estimate unbiased treatment effects. All right, that's all I have for you this week. I'm looking forward to our Q&A session on Wednesday.